Great. Okay, so very happy to have everyone here today. And to introduce our speaker, Gareth Roberts from the University of Warwick. I think within this community, Gareth doesn't particularly need an introduction, but we're very excited to have him here talking about recent work on simulated tempering and sort of scaling analysis. So Gareth is happy to take questions during the talk. So please, we'll keep an eye on the chat and the Q&A as appropriate. And Gareth, please take it away. Thanks.
Thanks very much, Sam, and thanks to all you organisers for this nice initiative and for the invitation to come here and present to you today. Yeah, so this is really quite recent work with, and in fact ongoing work really with Jeff Rosenthal in Toronto, and it was very much motivated by work that we've been doing in parallel tempering and simulated tempering. But actually, and it's turning out to be somewhat more general. So the presentation today is going to be presented in a sort of slightly more general way. And at the end, I will give a couple of pointers to our sort of future directions that we're sort of looking at. The basic theme, a big question that we're really interested in is the extent to which non-reversible MCMC looks non-reversible. And what I mean by that is basically to what extent when you look at sort of high dimensional or complex problems in other ways, to what extent does the sort of non-reversibility get somehow washed out and the algorithms behave in some sense as if they were sort of diffusive in any case. Yeah, so that's the main sort of theme. There's obviously been a lot of hype, I mean justified hype, I think, about non-reversible MCMC methods in recent years, and we still, I think, are only beginning to understand the extent to which they're better or perhaps not better than other kind of methods. Okay, so why is it that I mean, probably most of you have seen something on non-reversible MCMC by now, but just this is a standard kind of story really, that reversible MCMC or reversible Markov chains are very well understood mathematically. They've already provided fantastic algorithms for us like Metropolis Hastings, etc. And of course they work very well because they just rely on local computation, and all that's very nice. But it's been known for a long time that non-reversible Markov chains very often converge, and this is a rather vague statement, but they converge more rapidly than, in some sense, reversible alternatives. And I just put a sort of some of the I think there's a lot more references I could have put in there, but there's a lot of literature really that's been pointing to the fact that non-reversibility in some sense can help in terms of mixing of Markov chains, and that ought to be something that's useful for the MCMC community. But it's really taken quite a while for people to figure out exactly the best ways of doing that, and the sort of first steps in that direction, probably this paper at the bottom, the Diaconis, Holmes and Neal, using the lifted construction, and we'll be talking quite a bit about lifted constructions later on. Of course, I mean non-reversibility has always been on the sort of wish list of MCMC and sort of standard Hamiltonian MCMC or hybrid Monte Carlo algorithms. They themselves have a sort of non-reversible character, but in fact, there's certainly the standard way of implementing these things retains kind of reversibility. So even so, actually constructing non-reversible MCMC algorithms is not necessarily a kind of a trivial thing. In fact, it's only sort of really fairly recently that I think we've got sort of usable, potentially practical algorithms that can work in this regard. Okay, so if you just look at the, can you see my mouse, by the way? Because I can use that too. You can. Excellent. Thank you. So I've got here at the top, I've got a red trace plot and a black trace plot from two Markov chains. I can't remember what the invariant distribution was, but I can tell you that the black one was a non-reversible Markov chain, and the red one was a reversible Markov chain. And you can kind of see there that in some sense the black one has managed to sort of traverse a larger sort of distance in some sense. So this is the sort of intuition into what we want to try and do we want to try and break down the kind of random walk behavior that afflicts many sort of MCMC algorithms and reversible MCMC algorithms in particular. We've also, it's very often suggested that we might want to use reversibility to help with escaping local modes, to have some kind of some kind of momentum that pushes you from one mode to another and gets you over the sort of energy barrier. And so there are various kind of motivations, sort of intuitive motivations as to why this idea is kind of appealing. And the basic idea is we want to have some kind of momentum and in order to sort of traverse the state space a little bit better. Of course, you've got to be very careful here because you've got to choose the right direction for momentum, and particularly in d dimensions. And one of the things about d dimensions is that actually, if you've got momentum, that's going to be a vector, and that only pushes you in one particular direction. So what about the other d-1 directions? What can you do about those as well? So it turns out that it's actually sort of not at all straightforward how to actually even try and construct these algorithms. Okay, so this is a toy example. This isn't really from Diaconis, Holmes and Neal. This is actually from this is very, very classical, very, very well known. It's the next slide that really is from that paper. But I'm just going to sort of talk about sort of trivial little problem that many of us have probably thought about. Suppose you're looking at a one-dimensional random walk on the integers between -n and +n. And I'm just going to do a simple random walk with an appropriate behavior at the barrier to make sure that I have uniform distribution to be the invariant distribution on -n to n. Okay, so imagine n is large, and how long does it take for such a Markov chain to mix? Well, of course, this is sort of a very well studied problem, and the sort of intuitive logic normally goes a little bit along the lines of this. Suppose that we run this chain for k steps. Then if k is not too large, then by the central limit theorem, we'd expect x at time t to be normally distributed with a mean 0 and a variance t. And therefore, its standard deviation only scales as t to the half. And so therefore, to have any chance of actually reaching the sort of the far reaches of this state space, i.e. close to -n or close to +n, we're going to need this sort of t to the half to be at least of order n. And that suggests that we need to make basically t to be at least order n squared. And it turns out that this is the correct order of magnitude if you look at sort of mathematically defined mixing time for this problem. Then the mixing time is order n squared. And that's a rather disappointing outcome for a Markov chain which had only order n states. Okay, and then this is the kind of classic kind of diffusive type behavior that one might try and sort of avoid in this situation. Well, how can you avoid it? Well, one way of trying to avoid it might be to actually have some momentum which pushes you towards one end or the other end. But in order for that momentum to actually be done in such a way so that you still have a uniform distribution, it took a while for people to actually to work out how to do this. And in fact, so the Diaconis, Holmes and Neal paper was actually not even the first paper to do this, but I think it was sometime in the late 90s that this was discovered, this lifting phenomenon. And so how does this work? Well, okay, look at the same state space. And now what I'm going to do in this case is I'm going to say, okay, when I'm in this kind of upper replica, I'm actually going to have a momentum to the right. And when I'm actually in this lower replica, I'm actually going to have a momentum that goes to the left. And I'm going to choose my probabilities according to 1 minus 1 over n to move according with the momentum. And if I don't actually move in according with the momentum itself, I will force myself to actually switch momentum and actually go to the other replica. Okay, so it turns out that if you do this in the right way and you do things at the sort of edges in the right way, this gives you a stationary distribution, which is the product of a uniform distribution on the two replicas, having probability half each, and also having the uniform distribution on the X space between -n and +n. Okay, but notice here that so we did a lot of things here which we might not be able to do in an MCMC application. In particular, we actually chose the probability of going up to be not just one particular value close to 1, but we actually chose it to be 1 minus 1 over n, a value which is obviously going to 1 at a particular rate. Okay, so if we try and follow this sort of intuition of the previous example, then we sort of see that actually you can get to if you're starting at 0, you can actually get to +n or -n, depending on what your initial velocity is, without changing direction, with a probability which is something like 1 over e. And that probability is not going to 0 as n goes to infinity. So in other words, you can reach the far reaches of this state space in time order n. And in fact, you can actually show, and that's what the Diaconis, Holmes, and Neal paper did, was to show that actually the mixing time here is order n log n, which is far more rapid than the result for the reversible case. So this is all very promising and suggests that we might be able to improve on things. Of course, in this case, in this particular example, everything is stacked in the favor of the non-reversible MCMC algorithm. You started off with a state space that was long and thin. There was only one sensible direction in which we'd ever want to have momentum. That was, along either to the right or to the left. And also, we're allowed to actually choose our probabilities of actually changing the replica. In other words, I can actually choose the rate at which I jump between these two replicas. And in MCMC, it turns out that we don't have the freedom to be able to do this, and this will turn out to be an important issue in terms of what happens. Okay, so this is just, I'm not really going to be talking too much about other non-reversible MCMC algorithms, but just to say something about, where I think we are with them. There's a lot of hype about it, and I think it's very exciting, but there's still major challenges, particularly in sort of implementation and software for these methods, if they're going to become sort of competitive with the standard reversible methods which people are using in all the sort of probabilistic programming languages and so on and so forth. But certainly initially the results on non-reversible MCMC have been very positive. In particular, so I think a lot of the results about high dimensional scaling theory, how the sort of mixing times and other measures of conversion scale with dimension. Some of the early results have been really very, very encouraging in that respect. The second thing is principal subsampling, which offers a major advantage over subsampling Langevin methods. These methods scale very well with data size. So if you have very, very large data sizes, it turns out you can actually take very small subsets, possibly even size 1 of your data set, and still run a Markov chain which is not biased and has a mixing time which is of the same order. So there's some very exciting results about 2, which make the methods very, very suitable for large data problems. But I'm not going to talk about any of those. I'm going to really talk about 3, because we're interested in really sort of this kind of random walk behavior. And it's clear that basically in the right context, non-reversibility can break down random walk behavior. And that's sort of the idea that we want our non-reversible algorithms to actually do. So we're going to be investigating this in the talk today. Okay. Oh, and just to show you, in case you haven't seen, these are examples of what some of the PDMP methods that people are using. These are sort of zigzag and algorithms. The top 2 are just one-dimensional ones given as time series, and the one below is a trace plot of a 2-dimensional zigzag algorithm. And you can see that these algorithms have sort of momentum at different times, which pushes you in different directions. So in principle, you are getting this property of being able to break down the random walk behavior. But the question is, can you actually do that in a way that's kind of scalable to more complicated problems and higher dimensions? Okay, and now I'm going to go in a sort of slightly strange direction, which is probably not what you'd expect, because those of you that know about Peskun ordering will know that, that this is a result about reversible Markov chains. And you think, well, why on earth we want to actually look at things to do with non-reversibility? Why on earth are we actually looking at Peskun ordering? So for those of you that don't know this paper, the Peskun ordering it says the following. Suppose I have two Markov chains, P1 and P2, which are both reversible with respect to the same invariant distribution pi. But P1 is in some sense a slightly lazy version of P2 in the sense that the probability that I moves to J under Markov chain 2 always dominates that from Markov chain 1. Okay. And it's obviously, I mean, intuitively, it makes complete sense that P2 should be actually a better Markov chain than P1 in various senses. And this is the Peskun ordering. And one reason I really like Peskun ordering is it allows us to actually uniformly say things about estimating any quantities of interest. So for instance, if you have Peskun ordering between P1 and P2, and then for any function h that you're interested in, then if I look at the asymptotic variance estimating h under the first chain, it's actually bigger than or equal to, for the first chain, it's bigger than or equal to that for the second chain. So in other words, the non-lazy chain is always going to be better, no matter what functional of interest that you're interested in. Now, actually, Peskun ordering in itself, I mean, it doesn't seem very useful because it's a very, very strong condition to have where Pij1 is less than or equal to Pij2 for all I not equal to j. However, actually, it turns out that it's quite useful in many sort of situations. And even on its own, you can actually use it. And so a few years ago, Jeff and we generalized this to the context of reversible diffusions. And I just wanted to describe that now because it's this generalization to diffusions, which is the thing that we're going to be using in this talk. So suppose I have two diffusions, X and Y. Both of them have the same invariant distribution pi. And this time, the ordering is not going to be on all the Pij's, but it's just going to be a completely local one on the local volatility. So I want the local volatility of X to be less than or equal to the local volatility of Y, point-wise for all possible values of Z. So no matter where I am in the state space, if I'm running both chains X and Y, then the Y1 will be in some sense locally more diffusive than X. So the Y1 is wiggling around more than the X1, and that seems a good idea. And it turns out that it is the case that you actually get the same kind of Peskun ordering kind of result in this case. So you get that the limiting variance of estimating under the Y Markov chain is going to be less than or equal to that under the X Markov chain. For those of you that are interested, this results more than just a time change argument. I mean, you can't get this argument just from a time change because I'm not insisting here that the sigma functions are actually constant. If the sigma functions were constant, then this result is kind of trivial by a sort of a time scaling argument. But actually, the result there may be other ways of proving it, but the way we prove it is it's most natural to do it via taking limits from Peskun ordering results. And you can get things sort of multivariate versions of this, but anyway, I don't really want to maybe talk about that today. But so this seems sort of very intuitive, but it's not that useful directly because obviously we don't run diffusions. Our MCMC algorithms are not diffusions. But of course it is true, and everyone who runs MCMC algorithms knows that MCMC algorithms do look like diffusions. There are diffusion approximation results for pretty much all of our major algorithms, the Metropolis algorithm, the Metropolis adjusted Langevin algorithm, Hamiltonian Markov chain Monte Carlo, even Gibbs samplers, which at first glance don't look as if they look anything like a diffusion, PDMPs, and many other MCMC algorithms actually have diffusion limit results associated with them, expressing the idea that actually, if you look at their trajectories, they kind of look sort of diffusion-like. And therefore, so if we can actually, so one sort of way in which we can therefore look at these Markov chain Monte Carlo algorithms is to compare their sort of limiting behaviors and try and use that diffusion Peskun ordering result in order to say which one we prefer. Okay, so the idea is to actually look at diffusion limits for algorithms and then to make comparisons using the contractibility that we have for diffusions, which we don't have for other classes of stochastic processes. Okay, now I'm going to sort of move back to a little bit closer to what we were talking about at the beginning. I'm going to talk about random walks again, but I'm going to add an extra angle to this. I'm going to talk about the idea of optimizing random walks. So I'll change the notation very slightly here. Now I have a Markov chain X, which is living on a compact interval minus k to plus k for some large k. Okay, and what I'm going to do here is I'm going to say, well, okay, so I'm going to move from x to x plus z, where z has a mean 0 and a variance sigma squared. Okay, but also sigma is going to come out in a different way as well, because I'm going to have a penalization here. I'm actually going to accept this move with a probability e to the minus h sigma, where h is an increasing function. Okay, so the idea here is that the larger the moves I get, the more I'm taxing this by giving myself a chance of rejecting it. Right, this is, okay, this isn't exactly in an MCMC context yet, but this is much closer to the idea that when we're actually making making larger moves, we're more likely to reject them. So it's a scaling problem about how big should we actually attempt to make these moves. And the simplest example, and in fact, that's all we'll need for the simulated parallel tempering example, is where X proposes a move to X plus or minus sigma. So in this case, we basically, we move plus or minus sigma, but then we only accept with this probability. Now, to make this into a lifted Markov chain, we actually have to change momentum every time that we reject the Markov chain. So we'd have to sort of jump down to the negative replica if this is the case. But at the moment, we're just interested in this as a reversible scaling problem. So we don't have a non-reversibility here. I'm going to make the function h, I'm going to put some regularity on this. And the only purpose for putting this regularity in here is to ensure that, that there isn't a trivial solution to this, that the optimal thing isn't to take sigma to be as large as possible. So I jump in one step from minus k to plus k. Okay. It will turn out that in interesting cases of interest, these are exactly what happens. H is convex, H is increasing. So I don't even want to be very precise about this question yet, but I want to somehow minimize how long it takes me to get from minus k to plus k. And maybe in doing that, I might be interested in mixing to stationarity to uniform stationarity. So the question is, how should I choose sigma? Okay, so I mean, so this is, these problems are being considered a lot, and these kind of mixing time problems have been considered a lot. But not normally in the context of the scaling parameter sigma, because a lot of the mixing time results for a problem like this are ones which basically will just give an order of magnitude result, and the constants are going to be important if you actually want to decide how bold you are in terms of choosing this sigma, which determines how big your jumps are likely to be. So the problem's not really even very well posed. I haven't been very clear about sort of posing what I really mean by going from minus k to plus k, but I don't think I need to. Maybe it gives enough intuition about what's going on. Okay, now I'm going to make the problem harder. And the reason for making the problem harder is because I'm going to make it a bit more realistic for MCMC problems. I'm now going to penalize big jumps much more severely. Okay, and so this is realistically what happens in high dimensional MCMC problems where if you make a big jump, you're much more likely to go to somewhere where pi is very, very different from the place you've just come from. And it turns out the natural way to do this is to say that the move is accepted with a probability which is exponential. And now I've still got the same function h here, but I've got a d to the half in here. So this d to the half, it turns out to be natural in lots of situations. It turns out you don't necessarily need d to the half. If you have something else, you get exactly the same kind of behavior. But d to the half just turns out to be natural in most cases, many cases at least. Okay, and now this is a very classic context here. We have to make small moves now. We have to make small moves, otherwise we're going to reject these moves very often. And how are we going to actually solve the problem of actually optimizing in sigma? Well, I can just use Donska's invariance principle, which basically says, okay, k is large. I'll speed up time by a factor of d here. And I'll basically make my step size proportional to d to the minus a half. Okay, so Donska's invariant principle just says this thing converges in a rather strong sense, invariance principle sense, to a Brownian motion, and the Brownian motion is essentially just speeded up by a factor e of L. E is a function of L. Okay, where b is Brownian motion and e is just equal to L squared e to the minus HL. Okay, so the nice thing about this is that we can now solve this. If we know what the function h is, we can actually solve this to actually determine what this asymptotically optimal strategy is, just by using the Peskun ordering kind of idea. Okay, so the volatility of a diffusion is essentially the proposed variance, which is proportional to L squared, multiplied by the acceptance probability of this. So this kind of factorization here, which was artificial in this example we've just talked about, but is also something that's very, very natural and happens most of the time in high dimensional MCMC, where whatever you do in one component actually is only one component of d dimensions. So it's very unlikely that that component will be the dominating only thing that basically affects our acceptance probability. So this kind of factorization is an asymptotic independence between the accept-reject event and what we do in any one individual component. Okay, so this optimization problem, so it has, because of the conditions we imposed, has a unique solution. And the nice thing here is that the solution is kind of local. So in principle, you can actually apply it separately in different parts of state space. And there's an example of that coming up. Okay, and so so for the random walk metropolis algorithm, for instance, the function h looks like minus the log of 2 times phi of minus sigma. And so this is, we get if you want, you can get things like optimal acceptance rates of 0.234 or things of this kind from these kind of problems. But I mean, that's just one thing you can do with these, but you can do other things as well. So for instance, if you're interested in Malatap algorithms, then you get different kind of forms of your penalty for mixing. And higher order Mala algorithms, if you know what these things are, look a little bit like this. And from those things, you can get other complexity kind of results under regularity conditions. So in green there, I hope you can read the green, is basically tells you this idea that high dimensional MCMC, not always, but typically the accept reject decision and the move in any one individual component become in some sense almost independent, and you're accepting and rejecting in some sense on some kind of amalgam of the behavior of all the other components. Okay, and obviously that's not going to be true, for instance, if you have kind of hard bounds and you have discontinuities and densities, but it's true a lot of the time under kind of reasonable smoothness conditions. Okay, but we wanted to talk about non-reversibility. So let's go back to the context of lifted Markov chains. And I'm going to give a slightly more general lifted Markov chain here, where I'm just going to have my probability of moving to the right given by probability A. If I don't move to the right, then I force myself to actually change replica and go to the replica where I'm going in the other direction. Again, we're going to assume that we're working on some kind of increasing state space, but I'm not insisting that A is equal to 1 minus 1 over n, because maybe I can't do that. Maybe because I'm in a sort of more rough environment in some sense, maybe I can't insist that I accept a move with that probability. Okay, so this is the setup. So what do we think happens here? Well, to recall that in the Diaconis, Holmes, and Neal example, we set A to be 1 minus 1 over n. But if I just fix A to be some number, maybe quite close to 1, but just fix it to be some number, I can still look at what the asymptotic behavior of this will be like. Well, if A is close to 1, what will happen? Well, I may start off here, and I may actually have a pretty good run where I may actually sort of have 5, 10, 15, 20 moves to the right. But then eventually I'll move to the other replica, and then I'll have to move 5, 10, 15, 20 moves to the left again. And since n is increasing, in some sense, no matter how many moves I'm moving to the right or the left, typically on one of these excursions, that's still going to become insignificant as n goes to infinity. So intuitively, we might expect that we don't get quite the advantages of the Diaconis, Holmes, and Neal problem. In particular, the probability that I start at 0 and I get straight all the way to n without changing direction at all, that's going to become exponentially small as n goes to infinity. Okay, so in some sense, the effect of momentum can get homogenized here. And so this is something that we showed that if you look at this problem, there's an invariance principle that you can get for this problem, which is completely analogous to the Donska result, which basically tells us that you converge to Brownian motion, again, speeded up by a factor of E of L. But this factor of E of L now is very much like the previous one, except now I have a 1 over 1 minus AL at the bottom here. AL is just the acceptance probability, given that we try these jumps of size L. So, sorry, I'm mixing my notation a little bit, but so this is essentially exactly the same as for the reversible case, except now I'm multiplying this efficiency by a factor of 1 over 1 minus AL. Okay, so let's have a look at, so what does that tell us? So this tells us that since that quantity E for the non-reversible case, this object here, is bigger than the corresponding thing for the reversible case, for all step sizes. So this is telling us that non-reversibility can't ever hurt and is normally going to be an improvement for us. If you wanted to maximize that expression on the previous slide, this expression here, okay, you can maximize it again, and you can maximize it to get the acceptance probability. And it turns out that the acceptance probability optimized is 0.38, okay, which is larger than the reversible case of 0.234, because essentially there's more of an incentive to keep going to break down that random walk behavior. Okay, so how should we compare these things? I mean, so certainly it's useful to know that for any scaling, the non-reversible one will beat the reversible one. But if we want to actually get some one number to compare these things, we should probably look at maximizing both of them and then compare the optima. Well, if I do this, then the advantage of non-reversible over reversible is actually relatively modest. And this is the curves that you get. If you look at these asymptotic efficiency curves as a function of acceptance probability, this is what they look like. So the red curve you see here is the reversible case, maximized at 0.234. And the black curve is the non-reversible one, which is now maximized at 0.38. The ratio between these maximized values is about 1.42. So it's always there, but it's actually a little bit more modest than we might be hoping for. Note also about this, because of this factor of 1 over 1 minus a, you notice that in the right-hand side here, where the acceptance probability is very, very high, sort of easy problems, you might think about them, then you gain massively by non-reversibility. But as you get to sort of harder problems, then you have to sort of compromise how far you're sort of jumping with the acceptance probability, and you get gains which are more modest. Okay, so what we're going to do now is in the sort of and the last 10 minutes or so of the talk, just to go through to parallel tempering. I'll say something about these algorithms. Maybe a lot of you already know about parallel tempering. I'm not going to say too much, but hopefully enough to give you some intuition into what they're doing if you haven't seen them before. Okay, so I mean, I've been doing quite a bit of work on these kind of algorithms in recent years, especially with these people, Jeff Rosenthal, Nick Torn, originally with Yves at Shade, and special thanks to Fernando, my student, who's done a couple of plots that I'll use later on. And we've been working on a methodology which we call the ALPS algorithm, which I won't be describing in this talk because I'm going to be concentrating on other aspects. But I just wanted to say that sort of all the things that I'm talking about here, you can apply them basically directly to other forms of parallel and simulated tempering, whereas I'm just going to be describing in some sense the sort of vanilla versions of the algorithms here. Okay, so the idea here is we're interested in multimodality. So an example like this at the bottom, where I have two modes. And the idea is that's hard to do using off-the-shelf just Euclidean MCMC algorithms. And so there's a whole host of algorithms that have been proposed to get around this problem. Many of them based around tempering, and I give some kind of references there. There's a lot more that's actually happened and going on. And this is the basic idea. The basic idea is that we look at heated up versions of our density, or actually in some cases, cooled down versions of the densities as well. But so basically this is essentially, you can just think of this as pi to the half, and this is pi to the quarter, or something of that kind. And the whole idea is that in this bottom distribution, you might realistically think you can construct, an off-the-shelf MCMC algorithm like an HMC algorithm or a random walk metropolis or something of this kind to mix adequately in this bottom distribution. But I'd be hard pressed to do that in the top distribution. So the idea is to use tempering to essentially have a Markov chain which moves not only around the X space, but also moving up and down the temperature space. This parameter beta is known as the inverse temperature. So essentially the idea would be that in order to go from this top red mode here, the idea would be not to try and move directly over here, but to actually move in inverse temperature space down to this inverse temperature at the bottom, to move over to the other mode, and then to move back up. Now, there's a lot of moving parts needed to actually make this kind of thing work, and I'm not really going to talk in detail about that today. But you can see that a lot of the problems that we've been talking about today do fit into this in the sense that, there is one crucial thing that we need to happen. If you want to get from this mode to this mode, it's completely essential that we actually move down to the bottom, to this temperature at the bottom, and then we go back up again. So being able to traverse from one end of the temperature space to the other end of the temperature space and back again is something that's an absolute must and completely essential for an approach like this to have any chance of success. And in fact, much of a theory that's kind of used here essentially just tries to model this as a Markov chain moving in inverse temperature space, and uses assumptions to say that essentially the Markov chains that we have either mix instantaneously or pretty rapidly, at least within each mode. So I've got a Markov chain that can mix in that mode, can mix in that mode, can mix in that mode. And it's only at this bottom that we try the more ambitious moves to actually move between modes. Okay, yeah, so there are lots of interesting problems here. One problem is, how do we choose the collection of inverse temperatures, B? Okay, so if we actually have too many of these intermediate temperatures, we're going to be spending all our time moving up and down, making small jumps. So this is just like a scaling problem, just like the ones we looked at earlier. On the other hand, if we actually take too few inverse temperatures, it's going to be very difficult for a simulated tempering algorithm to actually move between the different inverse temperatures. So there'll be a penalty, and the acceptance probability of a move between temperatures will be low. Okay, so there are interesting questions, and we might be interested in actually how should we actually choose the B, and how should we choose the B on the basis of the algorithm that I'm using. It will turn out that, for instance, that for non-reversible parallel tempering, simulated tempering, we should have a different strategy for choosing the B than if we have a reversible one. I'm doing for time, not too badly. Right, okay, so yeah, so the various moves that we want to make moves within temperature and also between temperature. And it's these between temperature moves that are going to be essential, and in almost all interesting cases are the sort of limiting factors for what makes this algorithm work. So one of the big problems also with simulated tempering in this original form is that we actually have to pick a normalization constant, even though we might not know what the true normalization constant is for each model. We have to do that in order to actually determine the relative heights of the densities at different inverse temperatures. And if we actually choose that, okay, so it's a quantity like the following, this integral here, this normalization constant. And if we actually get that wrong, then we can actually make big mistakes. So for instance, going back to this diagram here, if it turns out that we guess the normalization constant for this middle temperature badly wrong, and there's very little mass here, it will not allow us to actually move down here very easily, because it will be very difficult to move from the top temperature to the middle temperature. And conversely, it will be very difficult to get back up again. And for this reason, simulated tempering algorithms in this basic form are often sort of difficult to implement, because you've got to have some notion about how this normalization constant behaves, which can be guessed. So parallel tempering is an alternative way of doing this, which avoids the need to actually do this kind of guesswork, and essentially is an algorithm which has an individual particle at each temperature at all time points. So this is how it works. So we start off, for instance, in a setup with maybe the red setup here. Oh, sorry, I'll start off with the blue. I start off in the blue setup, so I have this is my particle in the high temperature. This is my particle here in the even higher temperature. And the parallel tempering move would essentially swap them over. So the blue particle would move to here, and this blue particle here would move down to here. So this sort of nice idea allows the normalization constant to just cancel. So that whole problem goes away in the parallel tempering world. Now, it turns out that parallel tempering can be a bit more difficult to implement. But if you look at its asymptotic properties and efficiencies, they essentially behave in identical ways to the simulated tempering one. So even though in practice you might want to implement the parallel tempering one, it's easier to actually state the results for simulated tempering because you've only got one particle to actually worry about. So that's why I'm going to sort of ignore parallel tempering for now. In practice, people often use a combination of parallel and simulated tempering. They use parallel tempering to start off with, and maybe to estimate your normalization constants, and then they use simulated tempering from there on. But in any case, I'm just going to talk about simulated tempering from now on. And in this paper with Yves Atshede and Jeff Rosenthal, we did actually show that parallel tempering and simulated tempering essentially behave like the same kind of asymptotic diffusion behavior under various kind of pre-mild conditions, it turns out. Well, in that paper, they weren't very mild, but you can do it under very mild conditions indeed. Okay, so we're going to just look at a simulated tempering example, and we're going to look at this kind of mixing problem from going down from the temperature of interest to the very hot temperature and then going back up. Okay, and I think what I'll do is rather than okay, so and we're going to be interested in this kind of scaling problem, which is the problem of actually choosing the betas. I think I've introduced most of that already. Oh, and this is just to sort of, this is mathematically how we set up B. We set up B here in the following way. I sort of say I have a function L, and this function L allows me to actually construct a sequence of inverse temperatures, the betas, in the following way. Given that I've got the ith inverse temperature, beta I choose the next one by subtracting L beta I divided by d to the half. Now, L is a suitably smooth function, otherwise this doesn't really make a lot of sense. And essentially, so I'm using this kind of smooth function as a way of doing the scaling. So as I basically go to higher and higher dimensions, I'll be making smaller and smaller steps. Then all aspects of this function L will become relevant. And the whole scaling problem will become essentially equivalent to choosing a function L. Okay, so if this L is generally a little bit bigger, it will be saying that at most inverse temperatures, I'm making slightly bigger jumps. Okay, so this scaling problem is not a one-dimensional scaling problem, but it's essentially an infinite dimensional scaling problem. And there's certain sort of things which we don't need to really go into detail. What is the minimum possible temperature? Where, in other words, the minimum possible inverse temperature, i.e. the beta value at which I'm confident I can actually have a mixing Markov chain, and I call this chi, and then we work in that kind of way. Okay, so this is just a way of constructing the betas. In practice, you wouldn't use this as a methodology for constructing these betas. You do something a bit more so practical. Okay, so this is the construction that we have, and our result, which we originally proved under conditions of independent components, and it can be relaxed essentially to a very, very weak condition, is the following. And I'm just sort of rushing to this now. Is that if you look at the inverse temperature, and I look at the limit as dimension goes to infinity, in an appropriate sense, then that limit looks like this horrendous looking SDEY. Okay, and that looks like a really horrible thing until I tell you that actually it's just a nonlinear transformation of Brownian motion. And I can't quite remember what the transformation is, but you can work it out if you're interested. But essentially, this is essentially just a nonlinear transformation of Brownian motion. And the whole point now is to say, well, I'm actually interested. I'm not particularly interested in what this limit process actually is. It may be interesting that it looks like a Brownian motion, but I am interested in basically the diffusion coefficient, because of that continuous time Peskun ordering result we had earlier. It turns out that all I need to do to maximize the algorithm is to maximize this term in front of the Brownian motion. And remember here that L here is our scaling. It's a function. So in order to write this out in one slide, I've had to omit all the arguments. L is a function L is a function of the inverse temperature, and I here turns out not to be a function of inverse temperature, but it is actually some constant related to, in some sense, the friction going between inverse temperatures, how much the densities change going between inverse temperatures. So in some sense, you can look at this and think this looks complicated, or you can look at it and say, all I really need to do is actually optimize this quantity here. And the other thing that's very nice about this quantity here is that you can also decompose it as L squared multiplied by the acceptance probability, because the acceptance probability is just 2 multiplied by phi of this quantity here. So this horrible quantity I, which we probably can't estimate or would be difficult to estimate, you don't actually have to explicitly estimate. So the decomposition that's important, therefore, is the volatility of a diffusion can be written as L squared multiplied by A of y, where A of y is the probability that I accept a move started from this value beta, this value y, I should say. Okay, so we get the same kind of factorization that we got from those toy problems earlier on. Okay, and so therefore all the 0.234 theory holds, and this is something which is kind of nice, and it turns out that you can actually prove this in even weaker conditions than the ones we did, and much weaker than for the Metropolis algorithm results. But what we're really interested in here is, can you actually do this for the non-reversible MCMC? And I'm probably running out of time, so you probably know what to expect, but I have to tell you how easy it is to implement non-reversible parallel tempering, and this was done, for instance, in a paper by some of our friends. And if you basically, when you're doing swaps to parallel tempering, if you swap on even iterations, you swap these lot at the top here, and on odd iterations, you swap these ones at the bottom, it can create this kind of cascade effect whereby a particle which starts here, here will move here if it's successful, and then next iteration it will move to here, and then it will move to here, and then it will move to here. So you get this non-reversible kind of behavior, and the idea would be to try and duplicate this nice behavior from the paper by Syed and et al., which is very nice work in this area, showing that parallel tempering can actually improve on the non-reversible parallel tempering, which is the one you have at the bottom here, can improve on the reversible one quite substantially if you have enough of these inverse temperatures. But let's try and look at it in terms of the context of optimizing both the algorithm type and also the step size. This is what Fernando, my student, did, basically comparing non-reversible, which is this sort of, the non-reversible algorithm is the sort of upper curves here, and the reversible one, which is the lower curves here. And this is strikingly similar to the plots I showed earlier for non-reversible and reversible Markov chains, random walks. And that's not a surprise, because the diffusion limit result for non-reversible parallel tempering is exactly the same as what we had before. We have this factor of 1 over 1 minus a on the bottom. So non-reversibility helps by this factor of 1 over 1 minus a. So it's exactly the same story. We get exactly the same efficiency, asymptotic efficiency curves, and exactly the same advantages. And so therefore, so you can sort of see that you are going to get gain with non-reversibility. Non-reversibility, you want to have slightly more temperatures, and you want to have a higher acceptance probability, but still the advantage is only sort of 1.42. But even if you get it slightly wrong, you'll have something of an advantage, and you're not going to make matters any worse. Okay, so just to finish with some conclusions, yeah, so parallel and tempering and simulated tempering and their variants are very popular. They've been massively successful in physics, as have many of these methods, of course. They're probably still the sort of go-to methods for most multimodal problems. And you can apply them to non-reversibility, and they can give you advantages, but you shouldn't expect too much in sort of high-dimensional context, because actually, ultimately, if you apply them in their optimal regime, that you're not going to break down the curse of dimensionality. One of the things that one of the things I should say about that, though, is that non-reversible methods in this context do have a tendency to be more robust. If you're targeting an acceptance probability of 0.38 as opposed to one which has an acceptance rate of 0.234, that brings with it an inherent stability that 0.38 is a little bit further away from zero than 0.234 is. And so therefore there are advantages of the non-reversible one in practice, which has been found by the people who have implemented and suggested these things. And the last thing is that one thing that we've done recently is we've been extending this to the sort of non-reversible Metropolis-Hastings algorithm introduced about 13 years ago or so by some physicists, it turns out that many of the results that we get here, you can extend to that context as well. You don't need, in any sense, the sort of uniform distributions that are intrinsic to the parallel tempering kind of results. The limit distribution that you get in the parallel tempering has to be the uniform distribution, because actually you had a particle in every single temperature, so uniform was the only sensible limit. But it turns out the uniformity is not really a sort of a crucial part of what's going on. So anyway, so there's a lot more to do on this, and thank you for your attention.